This podcast is on vapor pressure. Alright, so water evaporates. What that means is that water molecules go from a liquid to a gaseous state, quite common, and they also go back from a gas state to a liquid state. So when water does evaporate, it does apply a pressure. So here is gas molecules that are going, I mean, water molecules going back into water, and water molecules going into gaseous water. So gases are often collected over water, so the vapor pressure of water must be subtracted from the total pressure. Pressure of water at a specific temperature must be given. So here's a kind of a classic example of what this means. Okay, so we have a substance here, potassium chlorate, and we're heating it up. And it's actually going to decompose. So when it decomposes, pure O2 is going to go through this tube. Eventually, it's going to go into this beaker here, and this beaker was originally filled with water. There was no gas in here to begin with, but as the reaction proceeds, this begins to fill up with more O2 in here because that reaction keeps on going. The problem is it is not pure O2. There's also gaseous water in here as well. So as the O2 is going through this tube and collecting oxygen, there's also going to be water that's also turning into a gaseous form. And you cannot say what the total pressure is going to be oxygen in that container. You have to account for that water that's in there as well. So in this problem, total pressure is going to equal the pressure of oxygen plus the pressure of water. So you can probably find out the total pressure using a device, hooking this up, find out what the total pressure is. The pressure of water at a specific temperature, they usually give you a data table of that. For every single temperature, there's going to be a vapor pressure of water. And that's usually given to you, unless you're solving for it in the problem. But usually that will be given to you. And you're normally going to be solving for the pressure of oxygen in this case to find out what is the pressure of oxygen being exerted in this tube after all is said and done. So let's try an example that has to do with this type of device. Alright, so a sample of sodium potassium chlorate was heated in a test tube and decomposed by the following reaction. So just like our previous example, the oxygen produced was collected by displacement of water at 22 degrees Celsius and a total pressure at 754. So that's important. They're telling me what the total pressure is. The volume of gas collected was 0.650 liters, and the vapor pressure of water at 22 degrees Celsius and 21 degrees torr is this. So they're telling me what the total pressure is, not the total, but the pressure of water at this specific temperature is 21 torr, and they got this from a table. So they're giving this to you in the problem. Calculate the partial pressure of oxygen in the gas collected and the mass in the sample that was decomposed. So this is a two-part problem. So the first part is quite easy. So we know the total pressure, which is 754 torr. It's going to equal the pressure of oxygen plus the pressure of water, but that's given to us. That's 21 torr. So we do some simple math. You find out that the pressure of oxygen in that container is 733. So using Dalton's law of partial pressures, we found out that the pressure of the oxygen that's being collected, and again we're referring to this problem right here, this picture, it's pressure of oxygen found out to be 733 torr. Pretty simple so far. The last part of the problem was to find out how much mass decomposed. So here we set this up. Here's my equation. I want to know the mass of this in grams. I have the pressure, I have the volume, I have the temperature. This really becomes now a gas stoichiometry problem. And we're going to use PV equals nRT to solve for this. And we're going to find out how many moles of O2 is being produced. So go ahead and try that. Oops. Okay, this is going to be a podcast on water vapor. It's related to Dalton's law of partial pressure. So, water evaporates. What that means is that when you have liquid water, the water molecules right above the liquid are evaporating, are turning into gaseous water, and vice versa. So there's this kind of a thin layer of water molecules that are always above water, and they exert a pressure. So gases are often collected over water, so the vapor pressure of water must be subtracted from the total pressure. And pressure of water at a specific temperature must be given. So usually you don't ever have to calculate that unless that's the problem, just to calculate it. But usually you look in a table and it'll tell you exactly what is the vapor pressure of water at a specific temperature. And that will usually be given to you in some way, shape, or form. And different tables give off different types of units, whether it be ATM or torr. So let's take a look at what this a pretty good example looks like. So here we have an example of potassium chlorate, and basically we have it at the end of the test tube and we're heating it up. And what's going to happen is it's going to decompose into KCl, so eventually it's going to and break down into oxygen gas. So I'm going to produce O2 gas. The KCl will remain there, but the O2 will actually travel down this tube and it'll go all the way down, and eventually it'll start to bubble and form O2 in here. Now, bear in mind that this upside down container was originally did not have any gas here. It was completely filled with water until the reaction started. Then once the reaction started, the oxygen started pushing the water down. So that's what this is this is basically O2 in there, but not only O2 but water, because since water does evaporate, it's not purely oxygen, but it also has gaseous water in there as well. And we have to take that into account when we're calculating for some problem that involves that. So let's try a problem that involves this exact picture. So here, a sample of solid potassium chlorate was heated in a test tube and decomposed by the following reaction. So this relates to the previous picture. The oxygen produced was collected by displacement of water at 22 degrees Celsius and a total pressure of 754. So this is my total pressure. The volume of the gas collected was 0.650 liters. And the vapor pressure of water, so here they are, they're telling me the info that you probably look in a table, but here they're giving to you in the problem. Calculate the partial pressure of oxygen, O2, in the gas collected and the mass of the potassium chlorate in the sample that was decomposed. Well, the first part of the problem is pretty easy. Since we have the total pressure, which is 754, the pressure of oxygen, we're just going to use Dalton's law of partial pressure. Plus the vapor pressure of water that gives to it is 21 torr. So 754 equals x plus 21. You'll get pressure of oxygen to be, using some simple math, 733 torr. So we find out what the pressure that's being exerted by the oxygen, and the pressure of the water was already given to us by a table. So that was pretty easy for the first part. The second part is we want to find out the mass of potassium chlorate that was decomposed. So the way we tackle this problem is first write your givens in your equation. So I have the pressure of oxygen, I had the volume of oxygen, I have my temperature of oxygen. I'm going to use PV equals nRT to solve for my moles of oxygen. So I want to know what my moles of O2 is, and we're going to use this equation to solve. Now, again, bear in mind we need to convert our pressure to ATM to use these equations. So go ahead and try it and see what you get. So go ahead and click pause and calculate it, and what do you get for the number of moles of O2. Alright, so you should have it set up like something like this. And the number of moles of O2 I got was 0.0259. Whoops. Well, now that we have the number of moles of O2, this becomes just a regular stoichiometry problem. I have 0.0259 moles of O2 times, for 3 moles of O2, it's 2 moles of KClO3, and I gotta convert that, whoops, convert that to grams. For every 1 mole we get, whoops, 1 second. Alright, I get 122.6 grams of KClO3. You do the stoichiometry and you should get 2.12 grams of KClO3. So this is how much decomposed after that oxygen was produced. Alright, so I hope this helps with the understanding of water vapor.